Hello, everyone, and welcome to the next part of our competitive programming bootcamp. So, in this part, we are going to be covering some very crucial data structures for competitive programming or just general DSA problems. And this is in the chapter 4 of CSS book, as you can see. Now, a lot of this is going to be C++ oriented, but if you're following along with another language, what you can do is try to Google the corresponding alternative to whatever I'm teaching. For example, if I am doing vector, then you can search vector alternative in whatever language you're using, and you'll get something like, okay, so std vector. You can search, and then you will get something like this. So yeah, that's how you can follow along for another language, but for C++, that's it. So let's start. Now, if you want to do any data structure related problem or CP, which this series is about CP, but it helps with both. What you need usually is a dynamic sized array. Now, in C++, if you want a dynamic sized array, what you might have been doing is something like this. You take an input and then you create a array like this. And then let's say you take input. So let me just code it real quick. Scene AI, and then you let's say see out the first element. Let's just do create an array. And as you can see, it works. But there is a problem in this. This is not legal C++ syntax. What's happening here is that first of all, this n is not a compile time constant. It's a runtime constant because we get it during input. So we cannot actually use it for stack allocation of an array like this according to C++. This is a C99 extension or something. So first of all, this is illegal C++, right? And second of all, even if this was allowed, what if later on in the code you wanted to add a new element? How can you do that? You cannot. So if you want dynamic sized arrays, what you can do is you can use a vector in C++. So a vector of what? We want a vector of integers. Let's call it A. And what is the size? It was n, right? So just take input n as well. So create a vector of size n, and let's first of all write this. Right. Now let's input this. So for integer I equals to 0, then n I plus plus c in AI. And now if I run this, it works fine. And now what I can also do is a dot push back, let's say some number 456, and then if I see out a 4, I will get 456, because what pushback will do is push at the back of this array. So right now this array was like this, right? 1, 2, 3, and 4. So I push back 4, 5, 6. So yeah, that is vector, a dynamic array. As you can see, that's what we have been explained here. And if you want to iterate through this array uh, without this for loop, there's another option. What you can do is use a for each loop. So for integer x in, this colon is meaning in here, in a, what we do is let's just see out x. Okay, so this works just fine. So this is a for each loop, and yeah, and then before I go on to initialization, if you press a and then dot, you will see a lot of functions. So you can explore these to see more functionality. For example, if I write this friend, what I get is the first element, and they have mentioned it as well, the first element. Okay, then similarly there's also a back function. This will return the last element, right? So if I run it, I get 4. Okay, now initialization. So let's say you you want to create a array right in the code. You don't want to take input. So one thing you can do is obviously something like, you first, let's say you create a vector of size 5, and then you can do a dot, oh, not 5. Okay, I'll explain. So first of all, you create a vector a, okay, and let's say you want to add elements to it, you do push back, right? You can do it like this, or what you can do is give it a size of 4 initially, and then say a0 is equals to 1, a1 equals to 2, a2 equals to 3, a3 equals to 4. So when you define a number n here, it allocates enough memory to store this many elements, and you have those elements in the array as well. They are initialized with the default value. So the default value for integer is 0. So if I were not to do this, I will get 0. Okay. Now you can also initialize all elements with some x value. So let's say we make every element 99, and let's just print the entire array here. So yeah, x. Now, if you don't know what this auto means, auto is automatic type reduction. Instead of writing the type here, we just write auto. So yeah, we have this. Now, so this is one initialization. Another way you can initialize it is like this: 1, 2, 3, 4, and you will have the array. Right. Now, you might think, okay, so I can also do this, right? But if I print this, okay, wait, what? Uh, this is, I was about to show, okay, interesting. That's not what happens. Okay, whatever. Never mind me. Never mind me. Okay, I think if I do it like this. Okay. I think I know what the problem was. So I was about to show something interesting. So give me a second. So n- you can also directly give all the elements in the constructor like this. Okay, and this works. So instead of writing an equals to, you can just remove it and write it like this. And actually, it is a like a C++ syntax. So you know how you write integer x equals to 5. You don't have to write it like this. You can write it like this. Oh, oops, what am I writing? So you can write it like this. You can also write it like this. And this is the universal initializer. So it is a good practice to use this bracket because this works everywhere. Now, if you extend the logic and then try to create a array of size 2 like this, then you will actually run into what? Uh, I should have prepared for this. Ah, whatever. Never mind me. I was gonna show something, but I think it is a language version problem. Never mind that. Just learn that this is universal initialization. You can initialize like this as well. Okay. So we have a vector. Now, what? Okay. Okay. I messed up it completely. So what I wanted to show, right, was that if you do it like this, now you won't get, okay, yeah, so you get one element, right, which you might think is the expected behavior, but when you write it like this, what you get 5 elements, right? And what this curly braces usually do is call the constructor for you, right? So this behavior is different. So this is the ambiguous part that I wanted to show, that while the curly braces initialization is pretty much the best way to do initialization, here it is a little bit inconsistent, and it does not call the constructor but creates with std initializer list. I mean, it calls a different constructor. So that's one thing you can keep in mind. So yeah, I guess if you were more familiar to C++, it would seem more unintuitive why these two are different. Because if you have an object, right? Let's say you create an object A and you have some constructor, right? Like this. Then it is equivalent to creating an object like this. And that, and since these two give the same value, you might expect that these two should also give the same value, but they don't, because this is, let me show you the reason. Reason is that, so the reason is that if I go to vector, it has, okay, let's search initial, okay, list. Yes, so as you can see, it has a constructor with initializer list as well. So this gets prioritized over the normal constructor that we use. So here we are not, so here we are passing 5 in the constructor. Here we are passing an initializer list with 5 in the constructor. So that is why we get different behavior. So yeah, that's something I wanted to show. And then similar to vector, we have string. So we can have string s. So you can initialize it like this, and then just out s like this, and you get a print. Now, like I told you, you can also do it like this. This is also a valid construction. And then if you want to stay consistent, follow the best practice, you can write it like this. So yeah, we have string initialization. Now strings are not immutable, unlike Java. So s is equals to, let's say, s plus this. This wouldn't, uh, so this would not like this would not do it like we do in Java, where we have to totally allocate a new memory. We don't have to do that here. It just kind of appends there. A better way to do it is like this: plus is equals to. So the time complexity for this would be O3, or whatever the length of this string is. Now you should not do it like this, because this would have a higher time complexity. Reason is that you are uh, first of all adding and then assigning it. Basically they have a different what we say overload for the function. So for plus is equals to, we directly append whatever we are adding, right? However, if we do plus and equals to, then for plus we append and get a new string, and that new string is assigned to this string. So that is one difference I wanted to point out. But anyways, this works faster than it works in Java. So in Java, uh, this works as slow as this, but in C++ this is fast, and it only takes the time uh, it takes to append this much. Okay, so that was string. You can also like access string values at some index like this. So you can just print, and so on and so forth. You have substring function to create a substring. You can try to read it yourself, not a big deal really. And yeah, you can also try doing this. So write s, then dot, and then you'll have a lot of functions to explore. And if you don't understand a function, you can go to Google, say std string, and then write the function name, let's say a substring. You will get and then write C++ reference. You'll get C++ reference. So yeah, that was string. Now let's move on to the next data structure, and that is how much time it has been since I'm recording. 14 minutes. Okay. So set. So now we have, now what if, let's say we have a vector again, right? So in this vector, let's say we have things like this, 4, 5, 3, right? What if you don't want duplicate elements and you also want them in a sorted way? Then what you can do is use standard set. So this set, right? Whenever you add something to this set, okay, to add something to this set, you say insert, okay. So whenever you add something to this set, if it is a duplicate, it won't add a duplicate entry because set is a set of unique elements. You don't have duplicate elements in this. And another thing is that they are automatically sorted for you. So if you try to iterate through it, like for auto x, for auto num in x, let's try to reorder it a little bit. And let's remove this. Notice you get 1, 2, 3, 4, 5. So duplicates are removed and you get it in a sorted order. So these are the two specialities of a set, but it comes at a cost. So in vector, right? So in a vector, if you want to push something, that is O1, right? Okay, so if you have a vector, push back, this is an O1 operation, okay? So this is an O1 operation. And if you want to access any element, right? Or let's say V0, this is also an O1 operation. Now in set, this is actually if the size of set is like, let's say n, right? So this is O log n operation. Okay, so insert is O log n operation, and if you want to erase something from the set, let's say x dot erase, so you can erase it like this. This is also a log n operation. So yeah, this is the cost it comes at, and also you cannot really like know what is the index of some element, right? So for example, let me just try to run this first for, and as you can see, we don't have 4. Now, if I want to see if this set has some elements, so you can just check the count of that element. So let's say 4, right? Let's just print the count of this element, right? We will get 0. Uh, and if you want to search for some other element, you'll get 1. Now, the thing is, you know that you can know that this element exists or not, right? But you cannot know the number of elements that are smaller than this. Essentially, you cannot know its index if you were to visualize it in a linear array fashion. So because it is stored in a binary search tree data structure, so that is why you cannot know how many elements are smaller than this. For that, you'll have to iterate. So that would be on. Okay. So that's just one another drawback of using a set. Now this is that thing that to know the index or the order basically how many elements are smaller than this. To know that, we have another thing called uh, policy based data structure. In that we have a ordered set, but that I would cover in the next video. So yeah, that is set. Now if you want duplicate elements, you can just use multiset. So everything is pretty much the same, just the time complexity of x dot count will be higher because it is counting all the occurrences. So if you just want to check for something, you can say x dot find, right? So you can use either find, or what I prefer is lower bound. So if you watched my previous video, you would know what lower bound is. It just says find the first element that is greater than or equal to this element, this number. So we'll get some iterator. Now if this is first of all not at the end of this set, that is, it is not outside the set, right? And if its value is equals to 4, then I know that it exists. Okay. Otherwise, I can just print it doesn't exist. Now, you might be thinking, why such a roundabout way? The reason is having the iterator helps. So, yeah, that is that. And about that, I wanted to see if there's something. Yeah, whatever. So, we have set, and yeah, we also have multiset. So, as you can see, you can use find. I guess you should prefer find. I don't know why I use lower bound. I think it's just a personal preference. I don't know why it is a preference, but yeah, I guess you should use find. So now, what if uh, in instead of a set, right? What if you also have some value corresponding to every element in a set? So if you want to store kind of a key value pair, right? How can you do that? So okay, before I explain map, I want to show you another thing. So you okay, do I show that? Yeah, let me show you how you can use a map without a map. So if you don't know map, don't worry. Or I should actually explain map first. So sorry. So let's say you want key value pair, right? So uh, for key value pair, what you can do instead of a set, you can use a map. So the key behave in the same fashion as it behaved in a set. They are unique and they are sorted, and now they can have a value associated with them, like M23 equals to 234. So what it can be useful for is maybe keeping a frequency count of a array, like what are the frequencies of elements. So you will get the frequency. So for example, we have a vector. Oops, right. So if you have a vector, we can just iterate through every element of the vector and increment the value at the frequency, right? So fx gives us the value for the map in for why is my explanation so bad here today? So what this is doing, so if you want to access some key, right? If you want to access some key in that map, you do fx. Okay, so you use these brackets like you do in a vector, and then you can change it like plus equals to 1 or just plus plus, right? And then to iterate through it, you can say you can iterate like this. And now if you hover over this, you will get some weird looking type, right? So hover over this and you get it's a pair of int. So a pair of int. So what is a pair? Pair is just a data structure to hold two values. Okay, it can hold any two type of values. Those are determined by these types. So first value is a constant int. The second value is an int. So we can access them like first and second. Now the first value will be the key and the second would be the value. So you can do iterator the first, iterator the second. And this way you will print a frequency map of the array. As you can see, we have a frequency map of the array. So that's what map is. You access keys. So if you want to think of it as an analogous to a vector, in that sense, the indexing is happening by keys and the values are just what is present at that key. Now, this indexing, just like insert and delete in set, is O log n. And this is this normal iteration. Now, this was map, right? What else? Let's see. So yeah, you can also have a map of between string and int. So basically, you can have something like f of apple is 1, f of what orange is equals to 2. And if you print this, you get this. So you can have any types, right? This is how templates work. Now, if you're using C++ 17 or above, how do you know if you're using that? You can do like this. So G++, you say standard equals to this, right? That's how, if you compile like this, you will get standard 70. So if you are above C++ 70, greater than or equal to, then you can also do it like this. So key value. So you can just destructure like you do in JavaScript and outprint it like this. So that's another thing you can do. And auto actually does not auto actually does not copy the entire type. It does not carry over that reference basically. So even if this can return a reference, you won't be getting a reference here. You will be getting a copy. So what you have to do here is say reference if you don't want to copy the string and value every time. So yeah, that's how you can use by reference with auto. So that was map, and you also have m.count to check if a key exists. So if I want to check apple exists, I can say f.count apple. Okay. Now I cannot do f apple because if this does not exist, so what this syntax does is if this key does not exist, it will create that key. Okay. So if you're checking for existence, you don't use that. And then we have the iteration. So yeah, that was a map, basically a key value data structure. And you can actually create your own map from a set by having a set with pair int. Right. Whenever you want to insert a new element, key value, you do it like this. And let's say you want to increment the value at key 3. What you can do is get the uh, position or place or pointer to the place where the key with 3 is stored. So which what you're gonna do is a dot lower bound. So you oops, what am I doing? So yeah, this way you'll get the element that has um, that has the first element as 3 and the second anything really because it isn't minimum here. And then you will check if iterator. So let's dereference it to get a value. And then we just check that if this is equals to 3, then we have gotten the value, and then we just update according to that. I know it's a lot of garbage. I just wanted to show that you can actually use a set as a map. I don't know why would you do that, but you can do that. Okay. Now there's actually a faster conditionally version of set and map. They're called unordered set and unordered map. So in an unordered set, the insert and remove is actually just O1 because it uses hash map. Similarly with ordered map. But of course, if hash collisions happen a lot, you can get ON. And in CP, people can generate test cases that will hack your unordered set and make it explode, and you'll get time limit exceeded. So either don't use it, or if you want to use it, just search blowing up unordered map, and you will get this blog. Here you can read how to prevent that. So yeah, that was that. Now iterators. So if you don't understand iterators till now, that is fine. You must have had a like some understanding in which with which you can like use it, but don't probably properly understand. So you have the data structure, right? So excali draw. Okay. So in a set, you have, let's say, these values. Okay, 6, 7. So you have all these values in the set. Now they're not actually arranged in this order, right? They're not arranged in this order, but the data structure is actually storing them in such a way that you get this order. And how it does that is by using a binary search tree. So like maybe 5, maybe it is stored like this, right? So this is like not correct. Maybe it is stored like this. Let me go here. So 1, Free. Okay. I keep messing this up. So 6, 3, 1, 5, 7. Maybe it is stored like this in a binary search tree, right? So it can access them in in the sorted order, but they're not actually stored like this. So you cannot just use the indexing operator, because what indexing operator does is, when you have contiguous memory, you take a pointer, let's say here, and then you add some value to it, because pointer is a memory address which is an integer. So this is, let's say, 3000. Then you add some integer value to it to get to the next index. Okay. So when you do something like a2, what you actually do is you get the base address of a, right? Let's say that is 3000, and then you add it to 2 times the type size type. So let's, if it is an integer, you add 4. So you get that address and you just then dereference it. That's what this bracket mean. Okay. So, but that won't work here. Okay. So what you have is iterators, which will tell us what is the starting position, what is the next position to that, what is the next to that, and up to what is the end, so that you can traverse through them. Okay. So those are iterators, and they basically have a few functionalities, like uh, essentially you need to know like what is the next iterator to something. Mainly you might also need previous, but next is pretty much all you need to create an iterator. Now, to iterate through something, you first of all get the begin operator, and then you keep on incrementing it until you get the end operator. Now, this iterator is just a wrapper for a pointer. So its value is just a pointer. Okay. It has just one pointer, which when you dereference, you get the value. But when you increment it, it does not increment the pointer value, which is done in the indexing uh, behavior. It is actually overloaded to call the next function, by which it will systematically go to the next part. So that is how iterators work, right? Um, so I wanted to show something with iterators, but I'm not sure what should I show. Um, what do I show? Let's create a vector, or let's create a set. Okay. We have a set, and you see this for loop I'm doing. You see this. So I'm able to do this because this class, the set, has actually implemented the begin and end methods, right? So that we are able to iterate through that class. Okay. So that's why this function works. If you're wondering like how can we do it, iterate on a class, that's how we do. It has to have let's just check all the conditions. So conditions for each loop C++. Oops. How do I search this? Okay. Okay. How to have for each loop for custom class in C++. So if you search this, you get this, that you have to specify the begin, the end, uh, iterators, and you have to specify the const as well, because this is used a lot more than the normal iterator, but you need to specify both, otherwise you'll run into weird behaviors. So yeah, and you also need to specify the dereference plus plus and not equals to, because for each loop is a syntax sugar over a loop like this, where you start from iterator.begin, you go until iterator not equals to end, and you increment it. Okay. So that is why you have to overload the plus plus function, and then you dereference it and get this. So this thing what we have written, right? So this int x, this actually translates to for auto iterator equals to a dot begin, iterator not equals to a dot end, iterator plus plus x is equals to mhm. So this for each loop is like a short version of this syntax. So yeah, that's how you can have for each loop for your own class if you ever make. And that's why iterators are a very handy thing to have in C++. So yeah, and a lot of functions like we have sort function, right? Let's say we have a vector here, and let's say I want to sort this. To sort, I need to specify the beginning and the end operator and iterator so that the sort function can sort this range from beginning to end. And how do I specify? A dot begin, A dot end. And this way it will work on your custom, uh, what we say, custom class as well, custom wrapper for array or whatever you have as well. The sort function will work. Now it might be slow depending on how the access is, but it will work. Okay. And then similarly, you have some more functions like reverse. You can randomly shuffle. Oh, oops, where did I go? So yeah, you have reverse and random shuffle. And just like you had iterator for vector, you have iterator for set. And this is just the type of iterator, right? Uh, I use auto, but if I were to check the type, right? If I check the type, see, it is std vector int iterator. So yeah. Similarly, we have iterator in set, and we can iterate in set as well. And due to this iterator system, we are able to iterate over anything that defines these iterators, and that is why they are so handy. And then whenever you find, you can check if you have found it or not, like this. So yeah, that was it. Set also has a lower bound function like you can do in vector, and it is also an o log n. So yeah, that was it, I guess, for the basic data structure and data structures that you must know in CP. Now I didn't go through like how actually vectors are implemented, sets are implemented, because that is not of any concern from CP perspective. But let me tell you, set and map are implemented using red black binary search tree. Unordered set and unordered map are implemented using hashing algorithms, right? And what else? I think that's all, right? Vector is just array. So let me explain to you like how vector works. So in vector, how dynamic size work is, let's say you say I want a vector of size 5, so it will get a vector of size 5, right? And now when you add something to it, right? Let's say if it does not have space to add it, right? What it will do is it will allocate something of twice its current size, so of size 10, and then add the new element there, move all these elements here, add the new element there, right? And what? So, and then these are empty, but you don't get them in your v dot size function. And the reason is that they are in the capacity, but they are not in the actual size. Okay. So now when you add elements, since it has the capacity, it will just add them here. And when you run out of the capacity, it will allocate twice the size of this as well. So you might be thinking, if I do dot push back n times, what will be the time complexity? It will be on, and let me show you. So initially, let's say its size was capacity was 1, right? So it goes from capacity 1 to 2, then from 2 to 4, then 4 to 8, 16. So it goes up to n, right? Or whatever is the closest power of n, closest power of 2, nearest to n, right? So it goes like this. And so it has to copy every time it resizes. But when you add these, so n plus n by 2 plus n by 4 less than by 8, this is actually less than equals to 2n. Now, why is it less than equals to 2n? Again, you can draw the analog with the bits in a binary representation. So this value of this bit is more than the value of all these bits combined if they were all 1. Okay, so if they were all 1, even if you add all of them, they're less than this. Okay, so the sum of all this is less than n. So the sum of n plus something less than n is less than 2n. So yeah, and also you can use GP, but having some visual cues to recognize the time complexity is useful. So yeah, that was it, I guess. Now bit set and okay, no, that's not it. So bit set I will do in the next video, but first we're gonna do DQ, stack, and queue, and priority queue. So now, how do you have a okay? So how do you have a? I'm still not used to Mac gestures. It's been so long. So let's say you want a linked list, right? How do you have a linked list? You use something like this. You use a list, okay? So the time complexity you have for a linked list, right? For a forward linked list, the same time complexity you will have in this list because it is implemented by linked list, okay? Now, if you want a doubly linked list, what you can use is a DQ. No, not DQ. What was that? Oh, sorry. List is doubly linked list. So yeah. So we have list. So this is a doubly linked list. You can push back or push in the front or pop back or pop from the front. So you can add to left or right, but random access is not there. Accessing is on. So this list, then similarly, we have a DQ, right? So it is a dynamic array like vector, but we can have push back and pop back as well as push front and pop front like we have in a list. Okay. So that is what DQ is. So you can, so it's basically a double-sided queue. So you can push from front or back or pop from front or back. And now if you make it a little bit more restricted, you get stack where you can only push and pop, and that is done from the top. Then you have queue, right? Now here I'm assuming you have the basic understanding of push pop. I mean, what stack is, what queue is, but you don't even need to understand that. If you understood till DQ, let's go. So in stack is like stack is like stack is pretty stupid, really. So in stack, right? So if you have a stack and there's like elements like 1, 2, 3, 4, right? Now you can only push and pop from the top, that is right side. Okay, you cannot randomly access these things, so it is like a restricted vector. And then you have queue where now this is a little bit more useful, right? Now here uh, let's say this is the array, right? When you add to something, when you add something, it gets added here, and when you remove something, it gets removed from here. So first in, first out, last in, last out, right? So you have push and pop in this as well. So this is the stack and queue. And then we have priority queue. So the way priority queue works is, so let's say this queue was something like 314, right? So this is queue, right? If it was a priority queue, what will end up happening? So if it is a priority queue, what will end up happening is these will get sorted, and you will always, so whenever you add, right? Let's say you add 5, it will automatically get sorted according to the priority. And when you remove, you will remove whatever has the least or most priority, depending on how you like ask it to order. So initially it will remove the greatest element, but if you use something like this, so vector int then greater int, then it will remove the smallest number. So yeah, that was priority queue. We will use priority queue in Dijkstra algorithm. There's no need to actually learn this right now. Stack and queue you should know, and DQ. But yeah, now bit set, and should we do bit set in this video? Nah. So bit set and what is this? Policy based data structure we're gonna do in the next video. Comparison to sorting. What is this? Oh, never mind. So yeah, these two we're gonna do in the next video. That will probably a smaller video, but the reason I'm doing this segregation is because it makes sense. These are a little more basics, the ones I have taught, and then bitset and PBDS policy based data structure are gonna be a little bit more advanced and a little bit more unnecessary for now. Even priority queue is not that necessary. So yeah, now with this, you should be able to try more problems on code forces or code chef or ad code or wherever you are practicing. If you're not practicing and just watching videos, I don't know what you're doing. You should practice video problems like I said in the second video. So yeah, hope you like this video. If you did, leave a like, subscribe, and I will see you next time.